Thank you, Heidi. I think we can truly say that this journey we've been on with GSHA could be characterized as a marathon, if not an ultra-marathon. So right now we're pleased with where we're at and some of the products we're starting to put out and some of the procedures we've got in place. So it is a good opportunity to share some of that with you and also to think about some of the bigger pictures that we're considering. Within DNR, we have sort of a focus on looking at healthy watersheds, and certainly clean water is one of those elements of a healthy watershed. And just generically, as a department trying to find and use the best science to advance various initiatives, and again, certainly clean water. And clean water investments especially, what we're trying to do with the modeling is looking at a different type of model, a distributed physics-based model that that we can use within the cycle here. Where's my arrows? And that's primarily that we see the use of this model is in that restoration protection strategy and also in the characterization and problem investigation. And again, looking, as we all are, what are the appropriate or the best practices to put where. And certainly over this last day and a half, we've heard of a number of models, and what we're suggesting is GSHA, again, this different type of model, can play an important role in the overall evaluation of our clean water issues and solutions. What does GSHA stand for? Gridded Subsurface Hydrologic Analysis. It's a program developed by the Corps of Engineers out of their Vicksburg lab and physics-based, especially on the hydrology side, trying to do that very detailed evaluation of water as it moves along the landscape. And I was thinking, think back to Sean's presentation where he did have a very detailed network, and really that's what GSHA is trying to do, and do a very good job on the hydrology, not just on the landscape, but also once it gets into the channel system too. And I'll be talking about the distributed nature of it. We got into this when we hired Greg Agers, formerly with the Corps of Engineers as a drainage engineer, and he had been working with both GSHA and its predecessor with the model developer for quite a few years. And so we've been gradually working on this. And again, call out to my other colleagues, Dan Reinert and Simon Matata. Raise your hand. They're sitting over here. Don't be shy. And so the four of us, each of us are working part-time on this model development. So what I plan to do is not really go into the details of the model, not go into the algorithms involved or setting it up, but try and lay out again why do we think this distributed model can play a role. And part of it, Mother Nature's complex. And a lot of the models I've been using for really decades, in a lot of aspects, it doesn't do a real good job in really truly analyzing the effects of land use changes. In particular, once we get into the drainage category, looking at the things of the loss of floodplain storage as an example. We also certainly see it as a tool that can be used for targeting and analyzing what's the net impact of a bunch of DMPs. But also, as I was thinking about this presentation, there's room in here for some of the big picture questions that I think have been touched on today. And then finally, the whole interaction between the distributed model and informing a lump parameter model. Just on that first part of complexity of hydrology. And again, the focus we've had is on that whole concept of altered hydrology. What does that mean? What's the impact? How do we address it? I picked this slide of the hydrologic cycle off from the Illinois water survey and talking about the various phases. I know we've got some groundwater folks in here, and so ModFlow does a pretty good job on the on the bottom layer on the groundwater flow, but relatively poor job or very simplified method on surface hydrology. Most surface hydrology model is really only focusing right on the surface and the lakes and the rivers, and groundwater included in some type of bucket approach. GSHA works both on the surface and it is calculating a water table, so a little more complexity in there in dealing with it. But even these models are simplifications of the real world. And so there is this tendency, because WEPP, the hydrology is complex, and even much more complex here. You start considering the depressions in the landscape that grow in tile drainage. There's a lot going on. So the tendency of models is to try and simplify so we can get an answer. But when you simplify, what are you losing with those simplifications? As an example, and Dr. Wilson touched on this yesterday, is when we think of, this is the data coming from the Discovery Farm. Kevin Keener just gave a talk here a few weeks ago. Really, his findings from the river data collection efforts are the very same. Here's showing when do we have the most sediment loss off of our landscape in an agricultural area. And it's May and June. And again, what's the causes of that? And a lot of it is you've got the bare soil, you have a phenomenon of soil crusting, so you get very little infiltration, and so in a situation with not that much rain, you can get a fair amount of runoff and soil erosion happening, and the data is consistently showing it. What's our primary method we use in the calculations of hydrology is curve number. Again, I just mentioned that yesterday. Curve numbers, you really can't make those adjustments to a curve number. I don't know how you do it, to try and get at the fact that, yes, early spring, late spring, early summer, you do have soil crusting, you do have increased potential for erosion and sedimentation reaching your channel. It's a simplification, but it doesn't really always work that way. The whole picture of pulling a slide off of Mark Homer's pyramid. I like this framework, how we conceptualize placement of BMPs, Joe Magner's treatment train approach. But again, as he mentioned, a key of this really is this, it's easy to sort of focus on the typical BMPs, the washcloths, the grass waterways, the governor's filters. Can we reach our goals if those are the only practices we put in place? Can we reach our goals if we do not put a big emphasis on the soil health initiative? One of the case studies I'm going to be talking about in a minute is the Dobbins Creek. Cedar River Watershed District obtained one of the Solstad's targeted watershed grant programs, and they've identified 94 practices in the upper end of the North Branch. Is that going to be enough? And it says primarily their washcloths, their grass waterways, a couple saturated buffers. There's been discussions. The Watershed District is doing a really good job. They're all contacting all of these. They've worked with the landowners, with the producers, willing producers, but is it going to be enough? So when I'm thinking of, and I'm guessing the question will come up, the users of the data, certainly there's a targeting aspect in working with the locals, and Greg Agers is doing that in Shakopee Creek, and I'll be doing it here. But to me, there's another audience here. I would like to think Solstad management would want to know, is this approach a workable practice? How much benefit are we going to get with saturation of BMPs in this watershed? And again, we're talking about the ability of the distributed model to really analyze each and every one of, well, not every, just as a collection, putting them precisely into the model, and what is the impact of that collection of BMPs. Just zooming in a little bit closer. It's a lot of BMPs, but again, You notice there's a fair amount of drainage waves, but there's no DNC cover. 94 is a lot. We actually need many more than that here in this situation. When I first saw this, and I just got this shape file not that long ago, provided by the Watershed District. Oh my goodness, why isn't there one here? Well, going on Google Earth, there already are grass waterways in a lot of them. So the producers have already been putting in practices here. But again, really none of that soil health type initiative is part of this effort. They're working on it, but it's not part of the effort right now. Talking about distributed versus the lumped parameter model. On the left, I'm showing output from a GSHA model, a distributed model. So we use LIDAR and keeping the topography within the model so we can have that at a very fine resolution, the flow of water over the landscape. And here, this is the Bear Lake watershed, just 30 miles east of Dobbins Creek, near Albert Lee. Numerous, hundreds of depressions within that watershed. And in this case, I turned off the tile routine and allowed the model to let the individual depressions spill from one to another. Doing a long-term simulation, so it's showing how that water regime of a given wetland will change over time. And so fairly confident that in that type of situation, the model is doing a pretty good representation of a very complex landscape. And then also working with computing the shallow water table. And so when say I restore one or two of these or drain one of them, fairly high confidence that it's doing well. My understanding of one parameter model is how it works in the same situation, and instead of all these individual depressions, we're lumping them all together in a virtual wetland at the outlet of each sub-watershed, and then having various fitted parameters to describe how they fill and how they connect to the groundwater system. One's not necessarily good or bad. I'm comfortable with this at a Huck 12 scale. I cannot do this at we cannot do this at a Huck 8 scale. We need the lump parameter model to do the larger modeling exercise. Can we learn a little bit more about how, in this type of landscape, water flows and help inform how these parameters are done? We think so. Model limitations, there's a steep learning curve. Although when I say that, I think, well, if I can do it, anybody can do it. Any modeler can learn this. But it is a time-intensive work. It's very data-intensive in that we want the cell size to be as small as it can be. And typically, SLAM doing something at about a 10-meter scale. It's in the 30 to 50-meter scale. That ends up being a lot of cells in the watershed. And run times can be measured in days, if not weeks. So that is a significant limitation. Water quality features, I'm not going to be talking about that. Nutrients, I'm not a water quality guy. Haven't been, nor do I plan to learn it. But we are going to be working with John Ebert and Joel Mather and two of their students. They're going to be evaluating the models, the nutrient part of the routine, and kicking in their tires, looking under the hood, and then also doing a comparison with SWOT and the strengths and weaknesses of each in regard to nutrients. Small user community. 3 of the 4 people in Minnesota using the model are in this room right now. It would be nice if there were more. The St. Paul district is doing a little bit good. Key data requirements, the usual suspects. Again, LIDAR is a key part of our component. Land cover, And climate, we're trying to get find a resolution on our precip as we can get, typically 15 minutes to 60 minutes. We do use radar as needed. Case studies. I'm going to mention two discovery farms, work that Swan is doing, and also I've already highlighted the Dobbins Creek. And this is a discovery farm in Blue Earth County. That's both surface runoff and tile flow, so it's being measured in both. And just a plug for discovery farms, that data collection program is great. There's a lot of data there that we should be, as a larger community, as this group, using that data, trying to learn, peel off layers. What does all that data mean? What does it tell us about our programs and how we want to address it? It's a data source that should be used more. As an example, early on, look at this is measured data. On the top is rainfall for a given event. The dark line is the surface runoff, and again, you'd expect that. This is a very small, 20 acres or so catchment area, and you'd expect it to be peaking right when it's rain. And duration is an hour. It doesn't last very long. But what was really interesting to me is seeing the tile flow responding almost immediately with rainfall. And if you think of that wetting front of the soil, most data I've seen, other presentations, that response is more in that 10, 12, 14 hours later. Here we're seeing immediate. You know what does that mean? Well, yeah, certainly there's some type of macroporosity, preferential flow paths going on in this system. When we looked at the SLOMS calibration, arguably that looks pretty darn good. Looking at the black dash is the measured data for this period in 2012. Blue is the computed. He's certainly gotten the shape. We've only sort of missed, the peak here. But otherwise, the model seems to be doing a pretty darn good job of modeling tile flow. So once we get into the tile flow, then we can do the various analyses of what if situation. And again, we're computing a shallow water table, so we can look at a particular cell and look at the hydrographs here. And this is just an example of what that water table would be with and without tiles for that same period. And you can see why producers, where if you've got a high water table, if I were in this situation, I'd put in tile too. And there's a significant period of time in the spring that you would have had a saturated soil condition and pretty tough to grow crops in that. But there are obviously impacts. One thing that, as just an aside, everything that we're doing is very much dependent on being able to characterize the soil samples. And Dan has done a lot of research on the various papers, what's the literature say, because say, for example, a silt loam, how does that change with changing covers from corn to soybeans to perennial cover, how do those parameters change? And he's had conversations with both Bruce Wilson and Satish Gupta. Both of them recommended we use the WEPP, the Water Erosion Prediction Project. And as we understand it, these are the best of the best. Look at all the various data to try and come up with exactly that question. How do soil parameters change in varying conditions? And the key for us is both porosity and hydraulic conductivity. So it is interesting, as Salam is doing his work, we can sort of really hone in on how well is his calibrated results matching that WEPP and the other literature that we've got. So another site he's going to be working on, I think he's already started. Is that right, Salam? And to get busy, another site here in Cushman County. And I found it really, you can see that a good part of that field does have a cover crop. So what changes might we see in the soil parameters in this field? How can that then help us as we look at a larger scale model? Dobbins Creek, again, right now I've got two models built, actually three. I'll share the results from two. One is a larger model that I use to calibrate the parameters in the model, and then a smaller model, just about 1 square mile, that I'm looking at DMP, what's the impact of various DMP practices. I did cherry pick some results on my calibration efforts, and again, it was pretty darn good. The model does do a remarkably good job on the hydrology in this watershed. Is it perfect? No. But again, you can see the snow melt doing a reasonably good job. Base flow during the summer, reasonably good. This was the September 2010 was the event that flooded Ortana. But it's not perfect. And again, back to my previous comment and things Bruce was talking about yesterday. As I did a long-term simulation, some events didn't calibrate very well. And so the question is why? And again, certainly a good reason is here. This is a graph showing for measured data, estimated the total rainfall amount over the watershed, and comparing that to the direct runoff, measured runoff. And you can see for these events ranging from 20% roughly to almost 50%. So for a given inch of rain, if you're getting a lot more runoff for that particular event, you've got that potential for additional erosion. Especially that last one, May 13th, highlight those results. May of 2013 down in this watershed, it was raining almost every other day through the spring. And as the blue on the top, so you can get that sense, it rained a lot. I actually know of one of the producers in the watershed. He did not get corn planted. He got soybeans in the middle of June. So again, these events happening in May. This is showing the middle of May. It's a fallow condition. You do have that soil crusting. You do have additional runoff erosion potential during that time period. And what the hydrographs at the bottom are showing is the darker black line is the calibrated. Again, I had to significantly reduce the infiltration rates compared to my overall calibrated soil parameters in the bed. So that issue of, in this example, the issue of soil crusting, the changing conditions, the fallow conditions, increasing the runoff by orders of magnitude. Looking at DMP, this is an example of being able to do distributed modeling where we are doing a very fine-scale modeling. We can precisely place DMPs in a given location. Here on the top, showing location, and this is just sort of a hypothetical example I've done, putting in 12 walk stops. Well, we'll do a very good job on analyzing the net effect of those walk stops. On the bottom is showing the actual land use, and this would be existing, and the blue is already perennial cover. So it is a watershed that has generally a very good riparian corridor. But of course, in a modeling scenario, and if it's distributed, and I've already done it, I can vary the width of that essentially the buffer. In the situation where you can fine-tune what is the impact of, in my case, a 20-meter buffer, 40-meter, 60-meter buffer. So that is also part of the advantages of being able to look at things in a distributed manner. So what are the results? This is just looking at flow, and first focusing on the black line would be the calibrated value or existing condition. And again, two events. This is June of 2009. Using the WEPP as guidance, in this case, relatively easy to go back. Well, what would be the conditions if it were strictly in prairie conditions, where you would expect the soil parameters are going to change your porosity, all those other things, then your infiltration will be a lot higher. And using the WEPP as a guidance on how to change those. That's the red bar in here. You can see there's a significant change. Again, orders of magnitude difference between existing versus the prairie. And not suggesting that we go back to prairie conditions. That, to me, that's not the long-term goal in this watershed. But as we look at the results, and again, the green bar is those 12, the green hydrograph is the results of those 12 wash stops. There's roughly a 20-25% reduction in these flows, which is pretty darn good. But when you combine wash stops with the soil health, and they really, when you think about it from a hydrology standpoint, they really do work well together. You're reducing your net result is getting pretty darn close to your pre-land conversion conditions. Looking at, if you run a sediment routine here, sort of same sort of thing. It's pretty good wash. The reductions for wash cobs on the sediment loading of the channel, not bad. When you add soil health, it almost, to me, it looks like, boy, that could be a game changer. It could be possible from a hydrology standpoint. Again, I'm just looking at the altered hydrology part of this equation. Soil health, increasing that infiltration capacity, increasing that water holding capacity with the traditional DMPs, I think we could go a long way. Back to this one, what's the result of all of these? Well, stay tuned. I've just finished actually this week developing the model for the 10 square mile upper portion of the watershed, and next week I'll be adding these DMPs and working with the local units, with the watershed district, sharing those results. Looking forward to that actually. So it's fun, pretty easy exercise. And again, I'll be looking at the exact placement of those and how do they work. And I'll be looking at other combinations of the DMPs. Take-home messages. Certainly not suggesting that GSHA replaces any of the SWOT or the HSPS, but rather in the global toolbox that we have for looking at DMPs and implementation, being able to precisely place and analyze combinations of these DMPs, looking at those bigger type questions. Can we justify to the legislature for, say, the accelerated grant program? To me, there's value in approaching this type of modeling. And GSHA does a good job on the hydrology, targeting DMP analysis. We can certainly work with at the local level. And there's a GIS aspect to it. So to me, there's opportunities here to use the model and sort of a discussion tool with the various disciplines. Count me in on, especially from the hydrology standpoint, on the bandwagon of soil health. I'm not sure we can get there without it. The whole issue of cover crops, protecting the soil during the spring of the year. Tile flow, all those DMPs I noticed, I identified for Dobbins Creek, really none of them address the issue of tile flow. You increase infiltration, you increase tile flow. It's an issue, and what's the impact? I think we need more work. Does it have an impact on channel stability? I'm not in the camp that it increased flooding. No, it doesn't do that, not in this case. Can GSHA be a good tool to try and get at some of those issues? Trying to bring people and looking at all the impacts of tile drainage, not only downstream, but it does reduce surface runoff. We're hoping for good results from John Niebuhr as he explores the nutrient aspect, and it'd be great to be also able to bring in the nutrients into the equation. How's that for time?